Hello, and welcome to the Origins Podcast. I'm your host, Lawrence Krauss. In this episode, we'll talk to the geophysicist Dan Schrag. I first learned about Dan as he gained national prominence for his groundbreaking work on paleoclimate, particularly the striking snowball Earth hypothesis, now widely accepted, that the Earth froze over completely on several occasions between 600 and 800 million years ago. Since then, he's become a leading figure studying current climate change, as well as energy policy and technology. He directs Harvard's Center for the Environment and the program on science and technology and public policy at Harvard's Kennedy School. Dan presents bold ideas of what we need to do to address the inevitability of climate change, as well as mediate it. Our in-depth discussion will inform anyone interested in the complex political and scientific challenges we need to deal with to move beyond our current crisis to a more sustainable world. Patreon subscribers can find the full video of all of our programs as soon as they're released at patreon.com/originspodcast. I hope you enjoy the show. Well, Dan, it's good to be with you again, as always, here in your lair, as it turns out. There are so many things I want to talk to you about. Every time I'm with you, I learn something useful about the climate and the Earth. Let me ask you, I want to start with your origins, though. I want to start, what was it about geophysics, geoscience that got you, that made you do that rather than something else?
You know, it actually took a long time to answer that question for myself.
Yeah, good. Well, you can take as long as you want to answer it here, too.
I was an undergraduate at Yale, and I'd always done science as a kid. In high school, I actually spent 4 summers working in a laboratory of a neuroendocrinologist. My first paper is written about the angiotensin in the hypothalamus of the Brattleboro rat. So doing biomedical research, and I think everybody expected me to go to medical school. And I think that was just about the time where all my hormones said that I had to rebel. And so I did something different. And I think I had this idea that I would become a physicist. Mm-hmm. And I took a course my freshman year at Yale that was above the course that was normally offered for physics concentrators at Yale. Mm-hmm. This was a course for people with extreme physics and math preparation. Mm-hmm. And I didn't have it. And it was a very good life lesson that there are just a handful of people who are always going to be much better and much smarter than you. At the same time, I had taken a political science course on political theory and a modern philosophy course from Harry Frankfurt, and was totally inspired. But I couldn't quite give up science. And the master of my college, where I was living, said to me, he was a physics professor, one of your old colleagues, Frank Firk.
Oh, yes, I remember him.
And he was a lovely man. I don't know if he was a good physicist, but he was a lovely man. Uh-huh. And he said to me, you should really try geophysics. But I kind of thought about it in terms of political science and resources. I ended up being a double major in political science and geology and geophysics.
Turned out to be perfect in the long run.
Yeah, it turned out I didn't put much effort into the geology and geophysics side. Mm-hmm. I put a lot of effort into the political theory side, and loved it. But when it was time to go to graduate school, I couldn't quite imagine becoming a philosopher. I don't know why. Honestly, it was, I think, because I'd never imagined being an academic. But in the end, I went to Berkeley to study economic geology. And while I was there, luckily ended up meeting somebody, switching advisors and working on what I would call really basic fundamental questions, not these are about earth science, about how the earth works, that have almost no relevance to people whatsoever. What I was studying was how alteration of the ocean crust, a few kilometers below the ocean floor, how that changes the chemistry of the rocks and how we can measure it by doing some diffusion reaction models. So I was basically modeling fluid rock interaction in basalts. Pretty obscure.
Yeah.
What I discovered was that the changes in the chemistry of the sediments on top was actually pretty significant. And those that chemistry was actually used to reconstruct ancient climate.
Oh.
So my entree into climate was actually a very backwards. It wasn't that I went to graduate school to study climate change or to study the environment. That was the furthest thing from my mind.
But, it's kind of, I don't know whether poetic or useful or just serendipitous that I've always thought of you as someone, maybe because of a kindred spirit, thinking of the physical mechanisms and the actual physics behind not just climate, but the way that the Earth system works. And so that physics background, or at least that scientific background, has been incredibly important in my mind in what you've done and in your ability, therefore, to not just communicate to the public, but to be able to good science associated with climate change.
So I think there's two aspects. Mm-hmm. Part of the reason climate change is so interesting scientifically is that it's actually an incredibly complicated and fascinating scientific experiment in the context of Earth history.
Yeah.
And so the science itself is really interesting, even if it had no societal implication.
But it does.
But it actually does, and then that makes it a whole another aspect.
It's interesting because also in your own life, this beautiful marriage between science and politics has carried out, as we'll talk about, and I want to talk about science and public policy, which you've been involved in. But let's go. One of the big arguments that's given about climate change is, well, the climate always changes. One of the big denial arguments is climate changes and big deal. So the climate's changing now; it's always changed. And your work over much of your work has involved the historical understanding of climate change, in particular over the history of the Earth, not just over the last 50 years. And you first became known to me with the remarkable work on Snowball Earth. Just to give a sense of perspective of where we're going to go when we talk about today's climate, why don't you talk about the long-term climate changes and the things that have happened in the Earth, including Snowball Earth?
So what's actually interesting is that the Earth has experienced such an incredible array of different climate states over its history. And our knowledge of that history essentially gets worse and worse as we go backward in time. Mm-hmm. So, for the last 150 years or so, we actually have instruments. There are a handful of instrumental records that go further back, but it's, it gets pretty bad before about 150 years ago. Before that, we have tree rings and some ice cores and some sediment cores, and they can give us pretty high-resolution records back over the last few thousand years. Mm-hmm. And then when we go back over the last few 100,000 years, we actually have sediment cores from all over the world's oceans that give us, century or multi-century resolution going back millions of years. And we can actually take that back, over the last 65 million years. But as you start pushing it further back, a couple of things happen. The records themselves degrade because rocks get buried, they alter, they chemically alter. That was actually the topic of my dissertation. But in addition, essentially you're looking for a big signal. So when I moved, I taught at Princeton for 3 years after I left Berkeley and was working really on two timescales. I was working on sort of stuff that happened over the last 60 million years or so. And then also looking at corals. Corals grow like tree rings. They put down about 1 centimeter a year of growth, and we can use them to get records of El Nino for the last few centuries or things like that. So I was reconstructing coral records with El Nino, and then reconstructing El Nino with coral records, and then working further back in time, but thought that basically prior to 50 or 60 million years ago, it was hopeless. And then I moved to Harvard and started this friendship with a guy named Paul Hoffman. Mm-hmm. And Paul was a geologist who spent most of his career studying the Precambrian. Uh-huh. But he was an unusual Precambrian geologist.
And just for some listeners, the Precambrian is some 600-700 million years ago.
Yeah, it's before about 540 million years ago.
Okay.
And it is an interesting time period because it's essentially most of Earth history.
Yeah.
The Earth's 4.5 billion years old. Sure. So the first 4 billion years essentially is the Precambrian.
Yeah.
And it is the time, so the thing that marks the Cambrian is the appearance of lots of trace fossils. It turns out, as we look at the record, there are some fossils before the the Cambrian, many of them.
Yeah.
But at the time, this was an explosion where you saw all sorts of bioturbation and all sorts of an explosion in the fossil record.
In fact, if I'm right, of course, many people, because that's when fossils first were seen, for many people that early on, that was the origination of life. They didn't realize that life had gone much earlier than that.
That's right.
Yeah.
That's right. And in fact, some of the classic work by Harold Urey, the great chemist at the University of Chicago, early on when he was doing early work on carbon isotopes and oxygen stable isotopes, he actually wrote in a paper that, the carbon isotopic composition of organic carbon could test whether there was life back through geologic time because of the fractionation from photosynthesis. So I mean, amazing history there.
Yeah, yeah.
And I think at the time, the paleoclimate community ignored, frankly, most of the Phanerozoic, which is the last 540 million years. They really thought back to the Cretaceous, but not much before that, which is sort of the last 60 to 100 million years.
Okay.
When I first got up and gave a talk on the work that Paul Hoffman and I did on the snowball Earth, these were two glaciations that occurred in the Neoproterozoic, which was a period from about 750 million years ago to about 600 million years ago. That's when the glaciations occurred. And
just to make it clear, by glaciation, we're not talking about small-scale glaciation. We're talking about a snowball.
That's right. People said, how could you possibly work on this? We don't know anything about the Precambrian. This is, the rocks are so altered. How do you say anything? And the answer is, it's a signal-to-noise issue. Mm-hmm. When the environmental signal is so huge, it turns out you can see it above all of the complications.
And it'll come back because I want to talk about the Earth and other planets. But the fact that the Earth, which is habitable, certainly, apparently, at this point, was essentially frozen over in its history. I mean, it was just shock. I know it shocked me. I think it was very controversial. But that's going to be relevant to understanding the history and origin and nature of life in other planets in the solar system.
Well, I think, as you know, science is about storytelling.
Yeah, yeah.
We scientists sometimes don't like to admit that.
Yeah.
But it's true.
Yeah.
Good science is a good story.
I've said the greatest story. But anyway.
Yeah, that's right. And I think in all good stories, there are only a handful of themes. Mm-hmm. And one of the classical themes is catastrophe and redemption.
Yes.
Right? I mean, that happens again and again.
Yeah.
And I think, the mass extinctions, whether it's the Promo-Triassic extinction or the Cretaceous Tertiary extinction. So the meteorite hits, all sorts of things die, the dinosaurs get wiped out, but the mammals arise and look, here we are, right? What a great story of catastrophe and redemption.
Yes.
Similarly, it turns out that may actually be the story of the snowball Earth.
Yes.
That we're doing work right now that links those snowball glaciations, both that time and then about 2 billion years earlier, about 2.4 billion years ago, there was another pair of snowball glaciations.
Oh.
And both of these, coincidentally, occur right at the time when oxygen jumps up in the atmosphere. The overall pattern in Earth history was for the first 2 billion years or so, there was essentially no oxygen in the atmosphere.
Which, by the way, I mean, most people don't realize. And well, of course, for a long time, that Urey and others, I mean, people assumed the primeval atmosphere was similar to what it is now, or in many ways. And of course, what people don't realize is that it's darn lucky for life on Earth that there wasn't any oxygen early on, because oxygen would have essentially, I mean, life is slow burning, and oxygen would have basically taken all the organic materials and oxidized them, and which is what life sort of does.
Well, there's an interesting thing about, how much oxygen is too much oxygen.
Yeah, yeah.
But yeah, so we think that, there was about, 10 to the minus 6, 10 to the minus 7 of present atmospheric levels of oxygen in the early days. So this happened for the first couple billion years. Mm-hmm. So origin of life happens in that environment. A lot of people studying the origin of life they sometimes forget that it's truly an anoxic environment, and it's very different, possibly hydrogen rich.
Yeah.
Then around 2.4 billion years ago, there's very clear evidence of a jump in atmospheric oxygen. It's called the Great Oxidation Event.
Yes.
And the timing of it is almost exactly coincident. We think perhaps exactly coincident with this global glaciation, one of the snowballs. And then again, around 600 million years ago, we think oxygen went from something like 1% of current level. So after the Great Oxidation Event, oxygen is higher, but it's not like modern. It's maybe 1% of modern.
Okay.
So essentially, everything was still unicellular.
Yeah.
But you started to have algae. Instead of just prokaryotes, you had prokaryotes and eukaryotes. So what that means is cells with mitochondria, later on with chloroplasts. So it's more like our cells,
prepared,
but they're still single cells.
Yeah.
What happens? It's possible that multicellular animals evolved sometime in this period in the Proterozoic, but if they did, they were really tiny. They were like multicellular little amoeba things.
Yeah.
They were tiny little guys.
Yeah.
And the reason is because oxygen's only 1%. If oxygen's very low, you can't get big.
Well,
because you have a diffusion problem.
Well, yeah. And I mean, to make it even clearer, I think of it in terms of physics it's not surprising, but oxygen allows living systems ultimately to get about 40 times more energy than they would in the case of sort of photosynthesis or in a.
The key reaction there is actually if you try to eat food, if you're a heterotroph, and you try to eat food, so you take organic carbon and you try to oxidize it with something like iron or with sulfate or something like that, it turns out you get about 20% of the energy that you would get if you used oxygen.
Yeah, the point is that,
much lower energy yield.
Yeah, much lower energy yield. I mean, that's what life is
but
for
there's
people.
Plenty
it's
of
we're machines.
But there's plenty of anaerobic heterotrophs that do just fine.
Yeah.
The point is that if you tried to make a multicellular animal in low oxygen, so then oxygen jumps up 1%. That's plenty for using oxygen now.
Yeah.
Right? So a lot of the zooplankton and single-celled organisms would do just fine in that 1% of oxygen. But when you try to get big, imagine you're the cell in the middle of a cluster of cells. You don't get any oxygen, right? And the way we solve that in our big bodies today is we have a circulatory system.
Yeah.
But it's hard to evolve a circulatory system before you get big. There's a chicken egg problem there. So what we think happened was around 600 million years ago, oxygen went from 1% to something within a factor of a few of modern level. So it went up by a factor of 20, 30, 40, something like that. And that allowed everything to get big. And that's when multicellular animals happened. So in some ways, the interesting part of our work on oxygen and the snowball is that it was the glaciation, this environmental catastrophe, that actually changed the environment. We have a mechanism where the glaciation actually allows for a jump in oxygen levels.
Is it simple to describe?
Well, it's not that simple, but essentially what we found is that when you think about atmospheric oxygen, you have to worry about electrons. Turns out that you're talking about oxidation and reduction. And there are really only a few geochemical cycles that matter. You have to worry about iron, and you have to worry about sulfur, and you have to worry about carbon.
Yeah.
And when you couple those, what we found was that this very simple model we put together actually showed 3 stable equilibrium states. A very low one, like what the Archean was, essentially no oxygen. A medium one that was about 1% of current levels, and then a kind of modern level.
This is stable when it's glaciated. When it's
no.
Okay, before.
The point is that if you were in one of these states, the geochemistry, there are actually some very strong negative feedbacks that keep you in that state.
So you won't change, but you need something dramatic to make it change.
But it turns out you need a kick to get you from one state to the other. And we think the snowball was that kick. So if you actually, if I were to give you my version of the history or the evolution of the Earth and the evolution of life, it's first of all not inevitable that we would end up here.
Yeah.
It's very important because some people think that there's sort of this, direction.
Yeah.
And the answer is, you know what? Were it not for those snowball glaciations, we could still be in the Archean with prokaryotic cells with essentially no oxygen.
Yeah, it wasn't written. I mean, that's one of the lessons of all, I mean, from my experience of the whole universe, is a series of remarkable accidents. There's no way that we were destined to be here. It's a very fortuitous situation.
Makes the appearance of multicellular animals and ultimately humans even more extraordinary.
Yeah.
Because you realize that these glaciations didn't just happen to Earth history. Right. They aren't just an interesting mass extinction.
Yeah.
They actually completely shaped the evolution by actually changing the atmospheric conditions with respect to atmospheric oxygen, which changed everything. It allowed life to get
And
big.
I think that's what, I mean, in giving historical perspective, because we're getting to the present ultimately, the point is that we humans who live for such a short time in a cosmic sense or even a geological sense think of things as having always been this way, and it's natural to assume they've always been that way, but that the Earth is very dynamic, the climate is very dynamic, and the development of life and living systems depends crucially on sometimes subtle changes, and that's going to obviously be relevant when we think of our own future. And of course, what's the reason that that's not so intuitive is that these generally have taken place over geological time. And we're in a situation now where there are changes that are happening on a much faster scale that are unprecedented in the history of the Earth. But it's interesting to see that how dramatic the changes have been in the nature of life and the atmosphere and the chemistry of what's going on Earth. And
yeah, that's exactly right. I mean, at the same time, I think. Let's get into what's happening today and talk about the historical context for it.
Yeah.
You're right. It is unprecedented, and it's particularly unprecedented in the pace, right? It's the rate of change that's unusual. Yeah. On the other hand, a geologic perspective on this is healthy because the Earth is going to be fine.
Yeah, the Earth will be fine, exactly. And in fact, life, I remember writing when I was first learning, actually from one of your colleagues, Andy Knoll, I was learning enough to write in one of my books about the history of oxygen on Earth. And I was just learning. And it struck me, I think it's a characteristic generally that, of course, from a natural selection or evolutionary perspective, catastrophes open up a whole new window. So life, in some ways, in the long run, life loves catastrophes.
So catastrophe and redemption is this theme, right? Yeah. And you keep coming back to it, and it's fascinating. I had a conference a few years ago gathering a bunch of conservation biologists, people who study the science of conservation. It's a little bit of a funny field, but it's a very important thing today, especially. How do you actually conserve species, for example? And a lot of conservation biologists focus on species. And the reason I was gathering them was because I was trying to be a little provocative. What I wanted to do was challenge them a little to think about the timescale of climate change. One of the things that you understand, or that we understand from studying the geologic past, is that the timescale of climate change, most of the IPCC studies and the UN stuff, people look at 2100 or 2050.
Yeah.
They might go out to 2150.
Yeah.
Right? But remember that, of the atmospheric CO2, so when we burn fossil fuels, about 60% of the CO2 stays in the air, about 40% goes into the ocean and the land. That 60% that goes into the air, half of that is still going to be there 1,000 years from now.
That's of vital importance. I think that if there's one thing people should understand.
It's really important. People don't think about it this way, but nuclear waste, high-level nuclear waste, in 1,000 years, about 1% of the radioactivity is left.
Yeah.
Because most of it has short half-lives.
Yeah.
Right? So that's what makes it so nasty.
Yeah, exactly. That's why the stuff you worry about is the stuff that has short half-lives.
Right. So 1,000 years from now, nuclear waste, 1%.
Yeah.
CO2, 50% in 1,000 years.
And
20, and probably about a third of it will still be here 20,000 years from now. So the timescales are really long. We are changing the Earth, not just for a few generations, but for tens of thousands of generations of humans, if humans are so lucky to stay on this Earth for that long. So that's hard to get your head around.
Absolutely, and it'll become relevant. What many people say is, well, why, maybe this is a problem, but we have economic problems, we have other problems. Well, let's not worry about it now. Let's worry about it in 50 years. And the problem is, if you keep dumping it in there, dealing with it in 50 years becomes so much harder than now.
So let's come back to that.
Yeah, okay.
Because this conference was really interesting, gathering these conservation biologists.
Sure, okay.
And what I wanted to do was ask them, okay, so climate change, you're not just trying to save species from extinction.
Mm-hmm.
You know, so the conservation groups, you know, World Wildlife Fund,
Yeah.
many of the other NGOs
Mm-hmm.
that do species conservation and biodiversity protection.
Uh-huh.
You understand this is a multi-billion-dollar a year effort.
Yeah.
This is not small.
Yeah, yeah.
And I sort of felt like, you know, they're trying to save species from extinction. And, you know, if you think about this, you know, are you really trying to save species from extinction today so they go extinct a few hundred years from now?
Yeah.
Or are you actually really trying to preserve biodiversity?
Mm-hmm.
And if you actually take conservation seriously, in my view, in the context of the timescale of climate change, you should maybe think things differently. You know, maybe instead of worrying about this species of frog and this species of frog and this species of frog, you might say, you know what? I want to make sure we have frogs.
Yeah.
Right?
Yeah.
You know, I'm not saying that the efforts these are great organizations.
Yeah.
They do a lot of good work. And I'm not trying to belittle what they do at all. I'm just saying I think we actually need to step back and think about what we're doing and question, are there additional things we might be doing in this broader context of the timescale of this problem?
And this is one of the things I really have learned in my time with you that is relevant, is that we can't stop what's already started, and we have to start thinking about how we deal with it. And you know, it's not a matter of giving up. It's not a matter of saying let's throw up our hands and just, you know, keep driving, you know, big cars and not worrying about that. But we have to recognize that these things are happening and have happened, and we've put in, you know, what it is, or 50 gigatons of carbon into the atmosphere.
500, yeah.
Yeah, and over per year maybe, and that's there, and it's going to have an effect, and there are things we're going to have to deal with, like it or not.
That's right. So the interesting response of these biologists was fascinating. Many of them said, I don't care about these timescales because all the things we study are going to be gone in the next 50 years. It was I thought I can be dark sometimes.
Yeah.
These conservation biologists really had a dark view of the world. But what was fascinating was my friend Doug Irwin. Doug's a paleontologist at the Smithsonian and is a brilliant scientist.
Yeah.
And Doug said, you know, what are we trying to save here? Are we trying to save species? Are we trying to save? But he said, from a geological perspective, you know, what I had said was, I would love to try to avoid this becoming like the Cretaceous Tertiary extinction or the Permo-Triassic extinction. You know, people talk about the sixth extinction.
I was just going to say people talk about the sixth extinction.
I don't think it's true yet. I think it's slight hyperbole.
But there's no doubt that that species are disappearing at a much faster rate.
They absolutely are.
Humans have been, throughout their history, we've done a very good job effectively at causing extinctions.
But remember that, like at the Permo-Triassic, we lost like 90%.
Oh no, I know, but it's just
so we're not there yet.
Yeah.
But Doug said, you know what? Look what happened after the Permo-Triassic. Like everything recovered.
I was just well, I've often wondered that if especially if we got rid of humans, that there'd be an explosion of new.
So what's interesting is, and I realized, you know, applying sort of human values and human morality to geologic time and evolution is a very tricky thing.
Sure.
Because things, you know, catastrophe and redemption, you know, we're programmed to think catastrophe is catastrophic. It's terrible.
Yeah. Especially if it's us.
Right. Yeah. And it's more complicated than that.
Yeah. No, there's no doubt that we're changing the Earth, and there's a lot of species that are going to be extinct, but it's probably unfair to suggest that won't it will be true that will open up evolutionary niches for new species that wouldn't have been able to survive before. Now, that's often a very bad thing, because that we often find in the United States and other places that predatory species that are dangerous are now viable that weren't before, and then we're going to have to learn to live with that. But there's no doubt we're opening up, even as we change the environment, we're opening up new evolutionary niches somewhere.
That's right. So let's get back to the question of the sort of historical context for what we're doing today.
Yeah, it's good.
Because I think it's important to understand, you know, we actually know the historical climate for the last several million years really well.
Exactly. And I think that's an important thing too, because people say, well, the question is always, well, people weren't around. How do you know it? And the point is there's lots of evidence. But I think it's really important if we're really going to have a serious and intelligent discussion about climate change today to have that historical context. So I'm glad we've discussed it. Anyway.
So we, for the last couple million years, we had these periodic ice ages.
Yeah.
And we know a lot about it. Mm-hmm. They were driven by subtle changes in the Earth's orbit around the sun, changes in how tilted the Earth was, or its precession around the sun, and the interaction with essentially two main factors: ice sheets, mm-hmm. which can amplify climate signals because mm-hmm. when ice grows, it reflects more sunlight back to space and has a powerful positive feedback. That's part of the snowball Earth phenomenon too.
Yeah, sure.
And also carbon dioxide. So the carbon cycle is another positive feedback. And these things seem to have worked together to keep us in this relatively stable pattern of, fluctuation between glacial maxima and glacial minima, or what we call interglacials.
Let me interrupt for a second, just as when you talk about the reflecting sunlight into space and carbon cycle, what's really important, it seems to me, in talking about this to members of the public and sometimes politicians, is that this isn't always rocket science. The details are very complicated models, but the basic physics of energy flow is pretty straightforward.
That's exactly right.
And what's surprising is that it works. I mean, maybe not surprising, but when you see that these basic physics predictions work, there's good reason to trust them. So
yeah, I mean, the basic idea of climate change has been around for 100 years.
Yeah, I mean, it's just the energy in, energy out. It's not much different. I mean, that's not to minimize the incredible complexity of clouds and the way and where on Earth temperature will change and how it impacts on sea level and all that. But the basic physics of energy in, energy out, of which carbon dioxide is a part, is not rocket science.
No, absolutely not. And indeed, people sometimes forget our neighboring planet Venus, right? Which is very similar to the Earth in size and is about 460 degrees Celsius on its surface.
Yeah, exactly. Right? And
super hot. Why? It turns out most people think because it's closer to the sun. And it's true. Venus gets about twice as much solar energy as the Earth does because it is closer to the sun. But because it's so bright and reflective on the surface, if Venus had the same atmosphere as the Earth, it would be substantially colder than the Earth, which is interesting.
It is interesting.
The reason Venus is so hot, it's 460 Celsius. It's incredible hot. It's because it has an atmosphere almost 100 times thicker than the Earth, and 97% of that atmosphere is carbon dioxide.
Yeah. Okay.
So the greenhouse effect as a phenomenon is really not in question.
And was relevant at the early history of the Earth. The Earth would have been. I mean, the sun has been getting brighter. It was 15% less bright in the early history of the Earth.
Star,
and so we should have been frozen, except the carbon. And then there was a greenhouse effect that preserved liquid water on the Earth in the early history of the Earth. The carbon dioxide density was something like 10,000 times what it is now in the very earliest moments of the Earth, or something.
Probably not that thick, and there may have been some additional gases as well. But here's but the general idea is there's actually a remarkable chemical reaction. So there's a chemical reaction between carbon dioxide, water, which makes carbonic acid, and then rock.
Yes.
And that reaction, igneous rock, volcanic rock, and that reaction yields, essentially it's an acid-base reaction. So carbonic acid is an acid, and it reacts with the igneous rock and basically makes calcium carbonate or chalk or limestone.
Stores the carbon.
And so essentially that chemical reaction takes carbon dioxide out of the air and converts it to limestone on the ocean floor.
Yes.
What's amazing about that reaction, because that reaction is temperature dependent, that becomes a thermostat. So when the Earth gets too hot, that reaction speeds up and CO2 is drawn down. And when that reaction goes too slowly, volcanoes naturally Now remember, volcanoes are only putting out about 1% of what we're burning from fossil fuels. So it's not like volcanoes are a danger.
Yeah.
But they're doing it all the time. And the CO2 coming out of volcanoes is balanced by what is going back down as calcium carbonate.
It's this remarkable
and so it's
balance.
This incredible cycle.
Until life evolved. But
now what we're doing to it is really extraordinary.
Yeah.
We are perturbing it by a factor of 100.
Yeah, that's important. I think that, when people
say the Earth will take care of it, right? Again, these chemical weathering reactions, this reaction between water and rock and CO2 will happen and will take care of our problem.
Yeah, but on geological...
But it will take about 100 to 200,000 years.
Yeah, exactly.
So it's just not fast enough.
No, so I was going to say, people, when they hear about this natural thermal stuff, they say, well, the natural reaction would be, why worry? Look, the Earth's taking care of it. But it won't. But we're changing things on a scale that the Earth can't adjust to.
I think there's another aspect of global warming that, again, is relatively simple physics that people can understand. Mm-hmm. If you look at a pattern of global warming, what you see is that the Arctic's warmed a lot more than the rest of the world over the last 100 years. Mm-hmm. And also that the land has warmed about twice as much as the ocean. Mm-hmm. So, overall, the world's warmed by about 1 degree. Over land, that number's almost 2 degrees. And it turns out there's a very simple reason for that. When we plant tulip bulbs in the fall, you plant them a few inches down, and they're protected from the frost of the winter. Right? Since Lord Kelvin in the 19th century, he actually measured temperature down a mine shaft to study the diffusion through soils. So, he did all of these amazing experiments. He was interested in the age of the Earth from thermal conductivity.
Yeah, it's wonderful. I mean, that's what I always love about when I do physics, is that whatever question you have, someone has spent their life studying it. It's really kind of amazing.
It's remarkable. But when you think about this problem, it means that the surface of the Earth doesn't actually have a whole lot of ability to absorb heat. Mm-hmm. And the reason is not because it has low heat capacity. Rock actually has a lot of heat capacity. It's that essentially rock is, you have to diffuse. You're conducting that heat through a solid, and that's fundamentally slow. Yeah. That's why you can plant your tulip bulbs a few inches down, and they're protected from the winter freeze, right? Yeah. Okay. So, but the ocean is different. The ocean mixes. Mm-hmm. The upper 100 meters mixes almost instantly because of the winds and the churning. Sure. Deeper down, you have currents that mix it on slightly longer timescales, but decades to centuries. Now you're talking about the upper 1,000 meters of the ocean, and the deepest ocean, the 4,000 or 5,000 meters down, is mixed over 1,000-year timescales. But what that means is, if you had the planet completely land, and if we had no oceans at all, and we raised the carbon dioxide level in the atmosphere, like we've done by burning fossil fuels, the Earth's surface would heat up relatively quickly and achieve that equilibrium really quickly, because there's not much ability to soak up heat. Yeah. We have a world that's covered with ocean, right? 70% of our surface is covered with ocean, and it mixes. And so what you can think of this is, do the experiment. You're adding carbon dioxide. The Earth's trying to heat up, right? Energy's coming in, and the way you achieve that energy balance is by the surface heating up so that the radiation going out equals the radiation coming in. Exactly. But the problem is the oceans are cold. Yeah. And it takes a while to heat up because they mix that heat downward. And so essentially 90% of the energy from the greenhouse effect that's being absorbed by the surface of the Earth is going into heating the oceans. Where do we see that? We actually see that in sea level rise. So thermal expansion of water. And so in some ways, sea level rise is global warming. Yeah, and because that's 90% of the energy. Global warming is ocean warming.
Yeah, I want to decompress that a little bit for people, because I think a lot of people think sea level rise comes just from simply melting of ice, in Antarctica or Greenland. But the point is that the sea level rise we're seeing, when water heats up, it expands. It's just simple. And so
today it's about half, maybe a little less, 40% of the total sea level rise is due to thermal expansion. There is an important contribution from Greenland and from Antarctica. Sure. It turns out that over the next century, those are going to get much bigger.
Yeah, exactly.
Thermal expansion will continue, but the melting of the ice sheets is what we have to worry about, because they're the ones that can really add to the sea level rise. But today, global warming, it's happening, and people too often use surface temperatures to indicate global warming. You say, that's the tail. Yeah. That's not the dog. The dog is the ocean. Yeah. Right? And if you want to see global warming, measure the temperature of the ocean. What's incredible is that we actually have new technology now. Until 15 years ago, the way we measured the temperature of the ocean is we went out on ships.
Yeah, sure. I remember that.
Dropped
oceanographers.
Thermometers down on a wire and measured them. That's what physical oceanographers did.
Yeah.
Hank Stommel, the great physical oceanographer who was at Woods Hole and at MIT, Hank Stommel in the 50s, he said, oceanography is like trying to do weather forecasting with a handful of cars towing kites around on a moonless night with clouds so that you couldn't see into the medium.
Oh, wow.
That's essentially what oceanography was.
Yeah.
15 years ago, they started this program called Argo, where these floats, they actually are designed to sit at about 1,000 meters depth. And every 10 days, they drop down to 2,000 meters, and then they slowly rise up to the surface, taking measurements every meter of temperature and salinity. And then when they get to the surface, they beam the data back to a satellite, and then they sink back down to 1,000 meters and wait another 10 days.
Yeah.
We now, in a few years, we collected more data on the oceans than we had in the whole history of oceanography.
How many of these things are out there?
There are about 4,000 of them. And it's a huge international program. The U.S. is the biggest contributor, but we've certainly contributed much less than half. There are, I think, 60 nations that have contributed to this float program.
It's nice to see a global effort for a global problem. It's always nice to see that.
It has transformed our understanding of the oceans. And it's allowed us to see that the oceans are indeed heating up. And that is, to me, the real proof of global warming.
Yeah.
There's another dark side of this, though, which is that it means that if we were to somehow magically freeze the level of CO2 tomorrow, not emit any more carbon dioxide from burning fossil fuels, which is not possible.
Yes.
The oceans probably got another 1,000 years of warming because the oceans are not in equilibrium, right? The oceans are cold. They're soaking up this heat.
And they're going to still coke it up. And the carbon dioxide is still there. And
so if you think about it, the land gets to equilibrium pretty quickly. The oceans are lagging behind. And so we may have close to double the amount of warming we've already experienced already committed in the system.
Yeah. Okay. Well, that's a very important thing. But there's two points I want to take from this. One is that, even if we stop things today, there are going to be effects we can change. And two, many people think climate change is all based on predictions and models in the future. But it's happening now. It's based on data you can measure. And even if, a senator brings a snowball into the Senate, the point is that you make measurements of the ocean that are unambiguous. It doesn't matter whether it's cold today in Boston and, oh my God, there's no global warming because we're having a cold winter. They're real measurements that show you exactly what's happening unambiguously. It's not model dependent. It's not consensus dependent. It's not politically dependent. It's happening.
That's right. And the models we use, honestly, there are problems with them.
Yeah.
But it turns out it's really difficult. The Earth is a complicated system.
Sure.
And to predict accurately what's going to happen 100 years from now is really, really hard.
Yeah.
But when I teach about climate change, I actually don't even mention climate models till the end of the course. It's not, there are very important tools to try to test ideas and think about what the future might be like. But I would never use them to actually make a prediction of the future, or at least make sure that I understand that there's some big error bars. There's a lot we don't understand about the system.
Yeah. Okay. So let's go in perspective and talk about the changes that have taken place due to human industrial activity. What's already happened, the range of possibilities of what might happen, and then I want to talk about dealing with this through politics and
technology. That's for me one of the most interesting things about this problem. And I got to say, for me, this was partly very personal. 20 years ago, I was giving talks all the time about climate change from a geological perspective. So I would talk about paleoclimate, and I would talk about the ice ages, and I would talk about the Eocene, which was one of the last times when the Earth was very warm. And that would put sort of climate change in perspective.
Yeah.
And then I would end my talk. And I would sort of leave people hanging. And for me, I think the audience liked it, but it was very unsettling for me. I was like, this just feels cruel.
Yeah.
And so I started teaching a course, and I'm lucky enough to be here where I have lots of colleagues who know a lot about this. I taught a seminar with John Holdren for undergraduates for many years, and John studied energy systems for years.
John Holdren, by the way, was the president's science advisor in the
Obama administration. And he started the Energy and Resources Group at Berkeley in 1970, 71, 72, something like that. And John's just a fabulous colleague. And so we taught this course together. And for me, it was a way of learning about energy systems because I wasn't happy just studying climate change. I actually wanted to understand what to do about it.
Yeah.
And so for the last decade or so, I've taught a course for undergraduates where I actually make them design a low carbon economy. The first sort of 60% of the course is about climate and paleoclimate. So they learn all of the things we've talked about.
Yeah, sure.
And then we take a switch and we say, okay, so now we're going to solve the problem. And they have to design an economy. It's for the US, but we talk about the world as well. And we're going to design a low carbon economy quantitatively. And they actually see how incredibly difficult it is.
Yeah.
It's really not easy.
Yeah. Yeah, well, exactly. Well, one might think if it was easy, it would be done, but I'm not even sure of that.
It's really hard.
Yeah, because people just don't understand the risks. But yeah.
I think that's, to me, the fun part of this is not just studying the Earth system and not just studying the modern climate and the future climate, but actually thinking about the energy systems that interact with it.
It's interesting to call it fun. From a scientific perspective, it's fun. For the fact that society has to do this and there'll be incredible societal implications, it may not be so fun, but we'll see.
Yeah, I've got to say, I mean, you said this earlier, that's what makes climate change so difficult is because we always want to push it off.
Yeah.
You know, some people say climate change is the most important problem of our time. And I actually think that's exactly wrong. Climate change is the most difficult problem of our time, but it's the most difficult problem because it's never the most important problem.
Yeah.
That's what's so nefarious about it.
It never seems urgent. Yeah.
It's never
like
urgent.
The frog in the boiling water.
And and I think it's the combination of two cruel aspects of the climate problem. First, and this is me sort of thinking like a political theorist a little bit, but the first is that it's a global collective action problem. And we're really bad at collective action problems.
Global collective action is unprecedented in the history of humanity, in a sense.
The free rider issue, that is, you know, why should I pay money if I can sneak without doing it and let everybody else pay the money? You know, it's really hard. Yeah. Right? So you know,
moreover, why should I pay money when other people aren't? I mean, that's the other thing. Why should we be the first to have a carbon tax or something when other countries aren't? Why should we suffer?
That's right. Yeah. And it's real. And the problem is, it's real money. Yeah. It's real cost.
Yeah.
It's going to be hard work to fix this. So doing this globally we've never done anything like this.
Yeah.
By itself, that may make this the hardest problem in the world. But there's another aspect that makes it even worse. And maybe much worse. And that is just about every aspect of the problem has really long time scales. Yeah. We talked about the oceans, right? That they have centuries, maybe millennia of warming still embedded in them. The time scale of the carbon cycle, we talked about tens of thousands of years. What about the ice sheets? You know, my guess is we've already probably committed ourselves to melting of Greenland.
Yeah.
Greenland is equivalent to about 7 meters of sea level rise.
Yeah, well, okay, good. Okay, we're beginning to get these numbers that
I mean, as a physicist, you know, there's what I love about telling audiences about Greenland. Greenland is so massive, it has its own tide.
Oh, wow.
Did you know this?
No, I didn't know that about Greenland.
So Greenland has about 7 meters of sea level equivalent, meaning if you melted all the ice in Greenland, the Greenland ice sheet's about 3 kilometers tall. If you melted all the ice on Greenland, sea level on average would rise 7 meters. 23 feet or something like that.
And I want to step back for a second. We'll get, because when people talk, again, it's one of these things when IPCC talks about, there's a centimeter sea level rise or whatever, people think, well, who the heck cares about that? And and I remember when I first was exposed to the data, the thing that amazed me is historically, looking back, and this was from ice cores in Antarctica and in the Dead Sea, I guess, carbon dioxide temperatures have fluctuated, but sea levels have fluctuated plus or minus 80 meters in the last 500,000 years or something like that, I think.
Well, so the glacial interglacial cycle. So remember that, you know, 20,000 years ago, we were in a glacial maximum. Today we're in an interglacial, or the pre-industrial, we were in an interglacial. We're kind of a post-interglacial today. during the last glacial maximum, 20,000 years ago, sea level was about 130 meters lower than today.
Yeah.
And the reason was there was a big ice sheet over North America called the Laurentide. Boston, here we are, we were under more than a kilometer of ice, right? Very different world.
Yeah, it's a very, and that's, people need to realize that there have been changes in not, in almost historical time, in a sense that have been huge.
But they were still slow. So remember the deglaciation where the sea levels rose from 130 meters lower up to today, that took 10,000 years.
Exactly.
And so it's all about time scale. So Greenland melting. So let me just tell you about the tides of Greenland, because it's a cool little fact.
Let's get the tides of Greenland, and then let's talk about what happens when Greenland melts.
So Greenland, 7 meters of sea level equivalent, right? Yeah. So if you melt Greenland, sea level goes up 7 meters. Yeah. Let's imagine we melted a seventh of Greenland. Okay? Uh-huh. So sea level would go up 1 meter on average. Okay. Mm-hmm. But if you were standing at the southern tip of Greenland, you would see a sea level fall by 19 meters. And the reason is that the Greenland ice sheet is so massive, it actually gravitationally pulls the ocean towards it, just like the moon pulls the ocean.
So if it becomes less massive, it pulls it less.
It releases the ocean.
To the rest of the world, I guess.
Now, on average, the rest of the ocean is at a meter.
But that's amazing.
That's how big it is.
I never knew that is quite amazing.
But you sort of step back and you say, wow, it's really big.
Yeah.
And we are unleashing these kind of forces. There's a similar story about Antarctica. By the way, Antarctica is about 7 or 8 times bigger than Greenland.
Yeah.
So the Antarctic ice sheet's massive.
Yeah.
So we are, with the Ross Ice Shelf, for example, we could be committing ourselves to tens of meters of sea level rise. Again, that could be over many centuries.
Well, although you can see
it's something that future generations can't do anything about.
They can't, exactly. And we're committing them now. And I mean, I've been down in Antarctica, and boy, you can see the changes. It's
extraordinary. And the changes just in the last 2 decades in Greenland. And
7 meters, just so people realize. I mean, it may sound like, well, who cares? I'm more than 7 meters above sea level right now. But
actually, right here, we're a little bit less than 7 meters.
Oh, yeah, here in Boston. That's right.
Well, exactly. so actually,
in Cambridge,
right here, we're above 7 meters, but most of the houses where the undergraduates live are below 23 feet.
Just the
Florida,
effect
in all of Florida.
All of Florida. But forget Florida and us. Let's talk about Bangladesh. Let's talk about where billions of people live and are going to have to move.
Well, but let's talk about New York and Shanghai and everywhere, all the big cities in the world, they're all affected by that.
Although the rich, we're jumping all around, but I think it's important to hit some of these topics while you mention it. Yeah, New York will be a disaster, but New York also has resources. But so maybe you can imagine a big wall around New York. I mean, we could get Donald Trump started on that right now, but the third world, where and again, correct me if I'm wrong.
Let's not call it the third world. Let's call it the developing world.
The developing world, where especially in the equator level, which is poor and has huge populations, in my understanding, will also get the brunt of the problems having to do with climate change.
So Lawrence, I actually think I agree with that to some extent. I actually think the climate community has made a mistake in framing it that way.
Okay, interesting.
And the reason is that many people walk away thinking that climate change is about the poor people in Bangladesh.
Oh, okay. Yeah, okay. Which means that you don't worry about it.
It's really not about that.
Yeah.
There's a couple of things. This gets into the question of what some people call adaptation, what I call preparedness.
Yeah.
I think preparedness is a better way to talk about it because, first of all, I think adaptation sounds painful. Do you want to adapt?
Yeah, no.
Nobody wants to adapt, whereas preparing is very positive. That's what the Boy Scouts and the Girl Scouts do.
Well, a lot of this, look, let's face it, a lot of this is going to require words and selling because people are not naturally tuned to think about things on that time frame of children or grandchildren. People, the risk assessment, of course, in humans is just remarkably, through evolution, inappropriate on these timescales. And
our political institutions, our business institutions, everything we have does short time scale planning.
And also small risks compared to large risk. I mean, it was just, I had to change my plans to come here because of 737 MAX 8, which, as horrible as that was, there are tens of millions of people that fly in those planes every day, or were flying. And yeah, two
The
planes
risk is
went down.
probably still less than you taking an Uber from the airport to here.
Yeah, but we have quickly removed all those planes because there's a 1 in a million or 1 in 100 million chance of getting killed in them. But we're on a slow time scale doing things with 100% likelihood of changing, but we don't think of that as a risk.
So this gets into this question of preparedness and the timescale issue, and I think those two intertwine. I have a friend named Kelsey Worth who's organized something called Mothers Out Front, with the idea that mothers are particularly suited to thinking about long timescales in future generations, which I think is a very clever idea. I think we need lots of experiments like that. Yeah. But in terms of the question about Bangladesh or Indonesia or tropical countries, the developing world, it is true. The developing world is going to get hit hard. But it turns out the developed world is going to get hit hard too.
Yeah, okay.
And I mean, look at Houston or look at the coast of Florida, the Gulf Coast after Hurricane Michael. It's like a bomb went off.
Yeah.
So we are vulnerable too. Now, that's not to say that many people in the developing world, because they are so poor and they maybe have no place to go because of political boundaries, various conflicts. In fact, you may see new conflicts arise because of migration. Yeah. But here's the important point, that I think the question of vulnerability is interesting. In some ways, people who are very poor are quite resilient because they have nothing to lose.
Yeah.
Right? And that's not to say that in any way that I'm not sympathetic to the poor people in Bangladesh. Yeah. But on the timescale of sea level rise in Bangladesh, those people will move.
Well, but here's, as complicated as climate systems are, and from your experience in politics, human social systems are at least equally complicated. And when you have several hundred million people who need to move, there is zero doubt, at least it seems to me, that the socio-political consequences of migrations, the instability, the government instabilities, will trickle throughout the world. Yeah. And so the developed world is going to be impacted not just directly by hurricanes or sea level rise, but by the fact that there is much bigger instability, or at least drivers of instability, in the rest of the world.
That's absolutely true, and certainly the Pentagon has thought about that and done some important work.
I was just looking today, and this is not new, but it's still worth stressing that the same government, and we're the only major country in the world where one of the leading parties still denies climate change. That nevertheless, no matter what's being said by the Trump administration, that right now the military is preparing for it at an active level because they have to. And so the realities are there no matter what the politicians may say.
So in 2012, we had just had a heat wave that summer in the U.S. 50% of U.S. counties were in emergency drought conditions. And then that fall, in October, we had Superstorm Sandy hit New York and New Jersey shore.
Yeah.
And I don't know if you remember, but in the 2012 election, when President Obama beat Mitt Romney, Mayor Bloomberg came out as a Republican and endorsed President Obama because of climate change about 2 weeks before the election, or a week before the election. Now, I think probably President Obama would have won anyway at that point.
Yeah.
But it's important to understand that was a significant point. And I was serving on his Council of Science and Technology Advisors, and the president asked us for ideas. He said, I want to do something more on climate change in my second term, and I want your help. And so I was lucky enough to draft the memo to the president that we wrote on this topic. And the first thing we said was focus on national preparedness, which at the time was considered radical. It was considered, we were trashed by many climate scientists, climate policy people.
Because for many reasons, but it makes it, one of the reasons that people are concerned about is they think, oh, you're throwing up your hands. You're saying, let's not deal with climate change.
That's what George W. Bush said. We'll just adapt. We don't need to do anything. We'll just adapt.
Yeah, which is, of course, not just equally worse.
Now, we pointed out that was our first recommendation. Our second, third, fourth, and fifth all had to do with reducing emissions. Yeah. So it wasn't like we were giving up by any means.
Yeah.
But after these catastrophic weather events, we were spending almost $100 billion that year on climate-related damages.
Yeah,
we said, you know what? this is actually important, but there was another point that we made in that report that I think people have lost sight of, which is, and this may get to a little bit of human psychology and the way people respond to this kind of damage. Collective action, global collective action is hard. Yeah. Why should I do something if China or Russia aren't going to do anything? Long time scale is hard. Okay, I care about my children and grandchildren, but I've got problems now. Yeah. I'm not going to put money, pay money so that they can be okay. Now, that's all hard. What do people really care about? I actually think they care about protecting themselves, protecting their families, protecting their communities. That's very primal. So what we argued to President Obama was that if you actually focus on people's vulnerabilities locally, and it's different in Florida than it is in Boston, and different in Boston than it is in Colorado, and different in Colorado than it is in Iowa. So different climate impacts. Yeah. If you talk about sea level in Colorado, not so much.
Yeah,
right?
Exactly, yeah.
On the other hand, in Florida, that's a big deal.
Yeah.
So you have to think about what local vulnerability is and help communities prepare for climate change. That is fundamentally a positive thing, protecting your community, protecting your home, right? That's just a good thing. And by the way, it also kind of gets rid of the concern about attribution of storms. There's always, every time there's a big storm, people say, is it caused by climate change? And you sort of, climate scientists stumble all over themselves saying, well, statistically it's related, but we can't say that any individual storm, blah, blah, blah. And already the viewers have turned off. The fact is, if you're prepared, it doesn't really matter whether climate change caused the storm or not. You're prepared. It's a good thing.
Yeah, preparation. Right? And inevitably, again, it makes such economic sense because preparation costs so much less than dealing with after the fact.
If you're getting people to prepare, and in doing so, they're actually learning about their vulnerabilities, we believed that it was likely that people would say, you know what, maybe we should support some policies to actually fix this problem once and for all. Because the more I learn about this is not a good thing.
Yeah.
Right? If I'm in Miami Beach, I'm saying, okay, I can prepare, I can protect my home, I can build some seawalls, I can put some things on stilts, I can put some sump pumps in. But this is not going anywhere good. Maybe we need to stop this.
Well, yeah, although the problem, of course, is that it also, at least when we're observing the current political climate, it makes you susceptible to people who simply have other reasons for not wanting people to deal with this, from saying, well, look, these people are scaremongers. They want you to prepare for things that aren't going to happen, or prepare. They're attributing things to the wrong thing, and they're trying to get you to spend money, and because the government wants to spend money. And
how so does there are people like that? And we've spent some time.
There's a whole party of the people like that.
There are we talked to some of the physicists who are hostile to this.
Yeah.
When we were in Mexico together a year ago.
When you and I were, yes.
But the reality is, I think most people get it. In fact, the polls say 70% of this country actually is concerned about climate change.
But are you at all concerned about the fact that one of the people that we were with in Mexico, who was just totally hostile to any notions, is now the person who's President Trump's advisor on this whole subject?
Am I concerned about it? Not any more than I'm concerned about anything else going on in Washington today. I think the important thing is that, look what just happened in Nebraska with the floods.
Yeah.
I think you talk to farmers in Nebraska, you talk to farmers in Iowa.
Yeah.
They actually get it.
Yeah.
And I think that the tide is rising, but I think the important point is that I think we're ready for a big political transformation. And I think what this has to come is it has to become a post-partisan issue.
Yeah.
A few years ago, I spent some time with Representative Eric Cantor. Do you remember Eric Cantor?
Yeah, I remember Eric Cantor.
He was the House Majority Leader.
Yeah.
And he was very conservative. He, at least in the press, they portrayed him as anytime John Boehner wanted to make a compromise, Eric Cantor would pull him back to the right.
Mm-hmm.
And I spoke to Eric Cantor in his office about climate change. He asked me to come in, and I was a little surprised because I was on President Obama's Science Council.
Yeah.
And so, why are you talking to me?
Yeah.
And he said, we talked about climate change. He chastised me a little for some comments I made about coal. But then he said he liked how I talked about the problem and about technology. Mm-hmm. And he wanted me to help his staff design a strategy for conservative Republicans that would be acting on climate change not through denial. And I was a little surprised. I said, why are you doing this? And he said, number one, we've purged all knowledge from our party, so we don't actually have anybody to advise us on it. And number two, Republicans under 35 think we're crazy. And he saw the writing on the wall that basically the Republican Party needs to switch.
This is a really important point. I think you're absolutely right. One can look around, and I think people are ready for change. But
now remember, he lost his primary 3 weeks later.
He lost it. I know exactly.
So I never got to do this work.
And let me say, and I was a little concerned when you talk about this. Interestingly, when I was chair of the board of the Bulletin of Atomic Scientists, one of the things we did, we had an event in Congress where we talked about climate change and other existential risks. And I was saddened at the time that it was open to all staffers, and I was hoping. And what surprised me was that only the Democratic staffers came to that, and I was really surprised because I thought it would be a bipartisan issue of just learning about the science. And I was and by the way, since we should make full disclaimers, you were not only on Obama's science council while he was president. I was on his advisory panel when he was running so we have our connections.
No, but here's the interesting thing. I think that the path forward in this country, the real sea change will happen when both parties are competing for better solutions.
Yeah, but I also think it'll happen within its generational. I think you hit the point that the Republicans under 35, I think that what is clearly happened, and it's good, and in spite of the incredible amount of money being spent to obfuscate the issue, that generationally we're beginning to see, and young people be concerned about many things. And anytime young people are concerned about many things, I think it's a great thing. And that's a property of having grown up in the 60s, I think. But once you have a generation that wants to change it, it doesn't really matter what the politicians are going to do. And so are you encouraged? There was this young student strike here in this country. In I think it's Stockholm, there's a young girl there's all these, I'm not sure.
So I had dinner last week with the Sunrise Movement, which is the group who started the Green New Deal. These are incredibly thoughtful, interesting young people, 25 years old. The founder, a lovely woman named Varshini Prakash, fabulous. Now, at 25, is she an expert on energy technology and policy? Of course not. But what she gets, which frankly a lot of people in the climate policy community haven't gotten over the last 2 decades, is the urgency. She says, we need to do this now. We're going to do this in 10 years. Now, there are all sorts of technical reasons why that's not possible, and I can explain why that. You just can't. And the reason is the energy system of the U.S. and the energy system of the world, it's just too big, too much cement and steel. You can't possibly build all that infrastructure in 10 years. And they say, why not? And you know what? I think they are opening up an opportunity to do something way more substantial than anyone imagined. And I think that's really important to watch.
I think that you made a key point. That was that what we're doing now, what's already been done, forget what's doing now, is going to impact our children and our children's children. We have left them a legacy. And they're the ones who are going to suffer. Now, you can always say, well, if you care about your grandchildren, but it seems to me that therefore is the community of people who should be most receptive, because you're younger than me, but still we're not going to witness the most severe implications of what's already been done to climate. And so it seems to me that we really need to reach the young people, not just because they're the future, but because they're the ones who are really going to have to.
Yeah, I think we need to reach everybody.
Yeah,
young people unfortunately don't vote, and that's a terrible thing in this country. But
they will. But the point is, I guess it's true.
But it's funny. You know what happens, Lawrence?
Yeah.
Young people become old. It's really strange.
Yeah, I know it happens. But if they're radicalized when they're young, I can't help but think that the fact that I grew up in the 60s has impacted on my politics and in now that I'm in my 60s. Anyway, so that's one thing. I think
here I think there's a couple things to say about technology that's really important.
Yeah.
First of all, in 2009, when Obama came into office, we were in the midst of one of the most terrifying financial crises.
Yeah.
And most of the leading economists in the U.S. both conservative and progressive. They really believed that the whole financial system of the U.S. could topple.
Yeah.
And our economy, I mean, it could be a total collapse.
Yeah.
They were terrified.
Mm-hmm.
So we, remember, a Republican Congress passed a $1 trillion stimulus package.
Yeah.
Unbelievable.
Uh-huh.
Why? And Democrats bailed out the big banks.
Yeah. Yeah. Things you wouldn't expect on either side.
Things you wouldn't expect because people were scared.
Mm-hmm.
Recently, a radio show talk host said to me, well, did President Obama miss an opportunity there to do the Green New Deal? Because we had $1 trillion.
Yeah. Yeah.
He actually spent close to $100 billion on energy systems, which was extraordinary. But here's the difference. In 2009, the price of solar and wind were about 5 times what they are today.
Mm-hmm.
We have seen an extraordinary change in technology in terms of cost. 5 years ago, 6 years ago, Massachusetts, Boston was considering Cape Wind, which was windmills out in Nantucket Sound.
Yeah.
The Kennedys opposed it.
Mm-hmm.
They didn't like their view from Hyannisport being damaged. But a lot of people opposed it for one simple reason. It was almost 21 cents a kilowatt hour.
Yeah.
That's the wholesale cost, not the cost to consumers, right? You probably have to triple that. I mean, that was like 3 times the cost of the power they were competing against. Just this year, Massachusetts signed a contract with Vineyard Wind to build a 400 megawatt offshore wind farm at 6.5 cents a kilowatt hour. Factor of 3 lower in just a few years. So the point is that we have technology today that we didn't have then. Electric vehicles, which, still are too expensive.
Yeah.
But you know what? We're beginning to see a change. Not 2018, 2% of new vehicle sales were electric vehicles.
Yeah,
that's extraordinary.
Which is extraordinary given what a decade ago. Yeah.
So again, are we there yet? No.
I'm going to try and be the devil's advocate. What do you say? And I've heard this for some people saying, yeah, this is all good stuff, but it's going to get better. So why do it now? I mean, solar and wind will be cheaper 10 years from now. So let's wait till 10 years from now to do that. What do you say to them?
The answer is perhaps, but right now, offshore wind in Massachusetts at 6.5 cents is actually, substantially preferable to almost everything else. Just a few years ago, I had a student do a study of renewable energy choices in Massachusetts, and offshore wind or bringing wind from far away were far, far more expensive than building a cable up to Quebec and bringing hydro power down from Quebec. Yeah. But you know what? That's no longer true. Offshore wind has gotten really cheap. It's almost directly competitive with natural gas. And in the winter, we actually don't have enough natural gas pipeline capacity. And so natural gas power is really expensive. Yeah. And so in fact, offshore wind could be a very good deal. Mm-hmm. It's really competitive. So I think those things are really close.
Okay, what do you do about there are powerful groups with lots of money that spend that money to direct public opinion, much more than the research budget of the IPCC is spent trying to obfuscate this issue. And so these are rational policies, but rational policies aren't always enacted. Is there a way to get through this message through in a way that people...
So now you're talking about communication. Yeah. I think there is a way. I'm doing an experiment with a colleague of mine. A friend of mine is a chief marketing officer at a large marketing firm in New York. Mm-hmm. We've created something we're calling potential energy. And what it is, it's actually never been tried. Mm-hmm. What we've got about 20 of the world's best advertising agencies, all pledging to work pro bono, doing serious marketing research, like social science, coupled with creative work. These are the companies that do advertising for Nike and for Coca-Cola and for, these are the most creative minds in the business. And they want to work pro bono because they care about this issue. And we're trying to raise some money to actually produce spots. We're focusing regionally, so we're starting with Florida. Okay. But this has really never been tried. Environmental groups have used advertising agencies to project their message. But that's not quite the same thing as saying, let's look at the research and actually figure out, just as they do with products. When they take Coca-Cola, they're not marketing just with creatives. They're doing very careful research about who is the target audience and what is it that they're going to respond to.
Well, it's great they're doing this pro bono. It'll be interesting to see.
So we're going to see if we can try this. Again, to me, you have to take shots on goal. You got to try.
You just try
and try a lot of things.
See what works. We used to say, even in the nuclear issue, what will be the Sputnik moment? And people keep saying that, in terms of dealing with not just nuclear weapons, but other existential threats like climate change. Sputnik was somehow, it changed this country in terms of the decision to put resources into education and science. And
there's one other thing that's really important. Mm-hmm. Years ago, in 2004, I had an event at Harvard with Vice President Al Gore and Larry Summers. And it was a very interesting combination. Larry Summers was president of Harvard and had just stepped down as Treasury Secretary in 2000 in the Clinton administration. And Larry Summers got up on stage and said something I think that's very wise. He said, and this is in 2004, just after the Kerry election, losing to Bush. Larry Summers said, action on climate change is going to take a really long time, much longer than people think in Washington. But when it comes, it's going to come really fast. And the role of a university is to be prepared with a plan, because the staffers in Washington are not going to do the careful analysis and discussion and thought that a real plan for dealing with this requires. So we need the plan. And I think that's really sage counsel. Now, that plan needs to be constantly updated to different technologies and different things. 10 years ago, you wouldn't have predicted that solar and wind would have gotten quite as cheap as they've gotten. So it's changed everything.
Yeah, no, and I put my optimistic and my pessimistic hats on alternately. I hope that I'm not always optimistic that good plans will even if they're available will be.
So I actually don't like the optimism versus. I don't like the optimism pessimism framing, and I'll tell you why, Lawrence. I have a lot of colleagues in this field, in energy policy, climate policy, who say, I've heard them say, well, we have to give people hope. We can't let people despair. And I step back and I think about it and I say, you know what? I'm a scientist. My job is to observe the natural world with as few biases as I can. I try to shed all the biases I have. It's not that I don't care about nature. I care about all these things. But when I'm observing the world, I try to put those perspectives aside and see things as they are, as best I can.
Yeah, sure. And
right? And then describe it.
Yeah.
And to me, sometimes in my class, people say, boy, you sound so pessimistic. I'm like, no, actually, I think about myself as an optimist.
Yeah.
I just don't think that pessimism or that optimism based in delusion is very helpful.
No. I mean, what people deserve is reality. But when even we've done public events, I think is just what you said. The reality is dismal. But But what we don't want people to do is say that they can't do anything.
So there's one aspect of this that I also think some of the environmental NGOs get wrong, which is human capacity to adapt.
Yeah, absolutely.
Humans, what I have a lot of faith in, and maybe this is just faith, but I think there's historical justification for it. Humans are ingenious. We are the most innovative, incredible species.
Yeah, and I think a lot of predictions miss the fact that technology and human adaptation will do things you hadn't expected.
I've been giving talks about this where I sort of say, look, the timescale of energy systems, the timescale of climate change, they're all long.
Yeah.
They're many decades at least to many centuries to millennia. This is a killer problem. It's the collective action problem. It's the long timescale problem. Humans are really bad at that. But there's a great quote from H.G. Wells that I love. He said, "We are kept keen on the grindstone of pain and necessity."
Yeah.
And I think there's some truth to that. That's not to say that humans won't suffer. Many humans will suffer terribly, maybe even die because of climate change. And we need to take that seriously. And that's a terribly moral obligation we have to the future. But I also believe that the 21st century, because of climate change, is likely to be the most innovative century in our history, but not necessarily in energy technology. It's going to be in things like architecture. It'll be things like transportation. agriculture,
I hope so.
maybe even governance.
Yeah.
The fact is, dealing with climate change, we haven't talked about solar geoengineering.
Well, no, we're going to get there. I want to end with that.
Things like that require new global governance that's way beyond what the UN can do. And you know what? I actually think humans will muddle through and figure out. By the way, nature is going to get screwed.
Yeah.
Right?
Yeah.
The fact is, the natural world, first by human land use, and now climate change is going to come finish the job. That doesn't mean there won't be natural things. There'll be plenty of wild space and trees growing and birds and animals, but it'll be nothing like what...
It's going to be Earth 2.0 or 3.0, yeah.
That's right.
And I mean, in terms of adaptation, I think you're right. I think with Sartre said that humans can learn to live in the trunk of a tree if they need to. But
don't underestimate how adaptive humans are.
Yeah,
humans are incredibly resilient. And by the way, there's sometimes when you hear people talk about climate change and you say, 4 degrees is the end of the world. And you sort of say, no, it's not. 50 million years ago, the Eocene, the Earth was probably 8 or 10 degrees warmer than today. And you know what? Had we been living there, we would have done just fine.
Yeah.
Now, the problem is getting from here to there in 1,000 years or 500 years or 300 years. That's really stressful, and a lot of humans will suffer. But there's nothing inherently unlivable about that.
Well, there's nothing inherently unlivable. Let me. I'm not so worried that physically it's impossible for humans to live under those conditions. What I'm more worried about is that the transition will cause instabilities that will cause human to use their weapons of mass destruction to end human life on Earth.
So I totally agree.
I think that's more.
The big risk is that our social systems and, when humans are stressed, often it's not very pretty.
Yeah. I think so. I think that's a more realistic concern than ending life. I often hear it saying this could end life on Earth. Well, it won't directly, but it could cause humans to take the action to do that. Before I want to talk about, we've skirted it, but I want to make it clear to people who haven't heard of this issue exactly what the change is in greenhouse gases. We really haven't said what the impact of human industrial activity is on that global historical timescale, just so people could put in perspective. We skipped it, and I think it's worth you spending a few minutes just giving that.
Sure. So 20,000 years ago, last glacial maximum, we have a kilometer of ice where we're standing in Boston and Cambridge. Carbon dioxide levels were about 180 parts per million.
Okay.
The pre-industrial, the interglacial, about 280 parts per million. And we've seen that cycle periodically over the last couple million years. When Dave Keeling started measuring CO2 in 1958, it was already at about 315 parts per million. So up about 35 parts per million from the pre-industrial level. Today, we're about 412 parts per million. So we are really going into completely unexplored territory.
That has not been seen on Earth in at least the last few million years.
At least probably 4 or 5 million years. And by mid-century, we're going to be well above 500 parts per million. And now we're talking about maybe 30 or 35 million years. So we're doing something extraordinary.
And it's really important to realize that when people talk about, you see parts per million, who the heck cares about parts per million? That the natural cycle has not anywhere approached this level.
That's right.
And moreover, as the natural cycle has varied over that, climate has varied tremendously. It's not as if sure, people can say, well, it never varied much, but who cares? But it varied a small amount, and climate changed dramatically. We're doing something that has never been an experiment that's never been performed, and at least in the last few million years.
That's exactly right. And we can look at the paleoclimate record to get a pretty good sense of how sensitive the Earth's climate system is to changes in CO2.
Yeah.
Because we have CO2 reconstructions and we know how much the temperature changed.
Yeah.
And the answer seems to be that the sensitivity, that is, per doubling of CO2, you get a surface temperature change of about 3 or 4 degrees. Now, what we've experienced over the last 100 years is only about, maybe 1.5 to 2 degrees per doubling, because we've only warmed by a little more than a degree, and we haven't yet doubled CO2, right?
Yeah, but we've got the oceans.
But that's it. So you have the ocean. So the other half is still coming.
Yeah, the other half.
So that's probably the resolution of that. So it's probably about 3 degrees per doubling. And just understand, 3 degrees doesn't sound like that much. But remember the difference between the last glacial maximum, sea level 130 meters lower, North America, half of North America covered with ice, the ice coming down to New York City. Completely different world, right? That was 5 degrees lower, colder, right? So we're talking about probably in the next 100 to 150 years being 5 degrees warmer. It's extraordinary.
Putting that, in context, I think is really important, because to me, when I talk to people, I say, well, we don't know what's going to happen, but here's what has happened. Here's what may be possible. Here's the context. Do you want to gamble? Do you feel lucky? Now, speaking of gambling, we've talked about adaptation or preparedness and the reality of the social difficulties. And some people might say, well, look, and you would still say, look, there's this carbon dioxide that's going to impact on our children, our children's children, our children's children, and on. Can't we do something to help them? And a lot of people are talking about geoengineering as a way to not just be prepared or live with this new future for the next 1,000 years, but change it and take it back, either somehow removing carbon dioxide from the atmosphere or doing things like blocking the sun or
understand that those two things are really, really different. And we have to, we've collectively, unfortunately, called both of those things geoengineering. And I think that's a terrible mistake.
I agree with you completely, because one involves, we know what will happen if you remove carbon dioxide. We don't know what's going to happen if you put...
So removing carbon dioxide from the atmosphere, first of all, people should understand that most ways of doing it are incredibly expensive.
Yeah, it's...
There are a lot of Silicon Valley entrepreneurs who think that they're going to invest in some magical technology. And what they don't understand is, even if it gets as cheap as some of the advocates say...
With $100 a ton is still incredibly expensive.
As long as some other countries are still burning fossil fuels, why would I pay to remove it?
Yeah. Okay.
Think about it. You're on a lake and your neighbor across the way is on the same lake. You both have houses on the lake, and there's some pollutant in the lake, and you're paying to take this pollutant out, and they're putting it in.
Yeah.
That's not going to happen. Okay. Right. And by the way, we're not talking about side payments of a little bit of money. Yeah. We're talking about, trillions of dollars per year. This is not a small amount of money.
Yeah.
So, but there's another point. Even if you did that, even if you could convince our country, for example, to spend Pentagon scale dollars on removing CO2 from the atmosphere every year, you'd need to do it for the next 100 years. It's inherently slow because it's on the same time scale that we burn the fossil fuels and put it in. So people forget that the world is putting in 40 billion tons of CO2 a year.
That's what I was saying, 40 billion, 50 billion. Yeah, it's just...
So the idea that even if you took out a few billion a year, you'd have to be doing it for...
Unless, of course, you're right.
Undoing it would take a really long time.
To make it practical would require some kind of sea change in technology. Now, it's not clear if the laws of chemistry and physics allow such a sea change.
The fact that Bill Gates and a variety of other entrepreneurs are putting money into these companies, a colleague of mine, David Keith, has a company like this that's building a factory to scrub CO2 from the atmosphere.
And we built a group at my old university.
I know. Yeah. You know what? I don't think it's going to amount to anything, but I love that it's happening. I have no problem with people's...
Me too.
But the argument, but if somebody asks me as an investor, should I invest in this because are they going to make money in the next 20 years? I'm like, wait a second. At least not the kind of money they're thinking.
Okay, so
that's the other kind of geoengineering is a totally different thing.
Exactly. Let's get to that other kind, because there's discussions of it, but there are concerns that at least that I have. So maybe you can...
So solar geoengineering, it's an old idea, right? It was in a presidential report to President Johnson. Okay, in the 60s. Okay, so this is an old idea. This was a favorite idea of Edward Teller, which is a good reason to sort of be skeptical of it.
Well, or be concerned. Yeah,
that's right. And there's certainly people irresponsible in this who say, oh, we should just do it because it's cheap. Not realizing that what we're talking about, and when I say solar geoengineering, I'm not talking about, so let's say there's different ideas. Some people say we can make low-level clouds that will reflect sunlight and cool the earth. Other people say we can put aerosols in the stratosphere and reflect sunlight. Other people say we could put mirrors in space.
Yeah.
Now, I'll tell you, I think the only thing worth talking about is the stratospheric aerosols.
Yes.
Not everybody agrees with me, but let me explain why. The space-based mirrors, lovely solution, unbelievably expensive.
Yeah, it just seems...
Not going to happen.
It seems very Star Wars-like.
Very expensive.
Yeah.
The low-level clouds have the opposite problem. They may be cheap, but the problem is the time scale of control is really short. They last hours to maybe a day.
Yeah.
Which means if you're going to use it to control the climate, you need to be doing it all the time.
In ways
no interruptions. The time scale of stratospheric aerosols, depending on how high you put them, is 1 to 2 years.
Yeah.
That's a time scale that you still need to keep doing it. But, if you have a couple weeks of crisis, you can...
the aerosols, I was talking about the low-level clouds. I think clouds and their impact on climate
aerosols with a couple sort of 1 to 2 year time scale, to me, that's the right time scale of control that's appropriate.
I'll buy that.
Now, you're absolutely right. We don't understand enough about exactly what it does. Remember, reflecting sunlight is not the same as reducing greenhouse gases.
Yeah.
The physics work differently. For example, night and day.
Yeah.
Right? The greenhouse gases work 24/7.
Yeah.
Because the Earth's radiating heat all the time and the greenhouse gases are working all the time.
Yeah.
Reflecting aerosols only work when there's sunlight. So it changes the day-night difference.
Mm-hmm.
There's all sorts of subtle ways that this is going to change the Earth. It's not going to perfectly compensate for greenhouse gases. It's imperfect.
Yeah.
But it is instantaneous. If you did it tomorrow, the climate would cool tomorrow.
Yeah.
Okay? So that's kind of cool.
Yeah.
The best studies we've done show that actually it works a whole lot better than most of us thought. That the best models we've done, and we've done many, many different generations, and people have tried to show all the problems. Is it perfect? No. In particular, there are changes in precipitation that may be problematic. But you know what? If you compare it to not doing it, and when I give public talks about it, I use Winston Churchill's quote about democracy.
Yeah.
That democracy is the worst form of government in the world, except for all the others.
Yeah.
I think solar geoengineering is the same. I think solar geoengineering is a arrogant, crazy, techno-fix, awful way of dealing with the climate problem.
But it may be the better.
Except for the alternative, which is letting the climate system happen. People say, oh, we should just take CO2. We should just remove the CO2. And you say, I wish it were that easy.
Yeah, if it were that easy. I mean, that's the obvious, we could do that, that's the obvious solution.
What is dangerous and what a lot of people get uncomfortable about solar geoengineering is what they call the moral hazard. The idea that by doing it, you reduce the pressure on reducing emissions. So people keep going. And that is a real concern. But you know what? To me, we're talking about human misery. We're talking about the end of nature. So you got to think of, drastic and here's the
problems.
Other point. This is a mistake that I think a lot of physicists made in the Manhattan Project. Mm-hmm. They thought they were going to make the decision on whether to use the technology. It's not our decision. And so I feel like so what we're doing at Harvard is we've created one of the first big research programs on this subject.
Oh, good.
And the reason is I feel like we have a few decades to figure out all the possible things that might go wrong. Mm-hmm. Already, for example, I think we've made a big difference. I think the research community, not just at Harvard, but around the world, if 10 years ago, if you were to talk about solar geoengineering, the way and if, say, somebody wanted to do it, say some country, that China or the US wanted to do it, they would inject sulfur dioxide or sulfur particles into the stratosphere. It would make sulfate aerosols, it would get oxidized, and reflect sunlight. But what we learn now is that would come with a very big risk of hurting the stratospheric ozone layer, which protects us from UV radiation. Yeah. So what we're talking about now is putting other types of particles, maybe calcium carbonate, maybe other things that actually might actually help the stratospheric ozone layer. Yeah. So that's the result of research. The point is, it's not our decision, but it is we have the potential power to help nudge the decision makers about how they do it and if they do it. And I think we need to study. To me, I've been very insistent that all the money we put into how to do it, an equal amount of money should go into what are all the possible ways it could go wrong.
Well, absolutely.
Because we need to essentially do a serious risk analysis of this.
And the problem, of course, let me say, the problem with all these things is that often what goes wrong is what you don't perceive. But the good thing.
But let's get a whole lot of good, smart people trying to think about all the problems.
So for me, the one solace is, as you said, is that it's got a half-life of a year or two. So you screw things up, at least you're not screwing it up for 10,000 years.
But understand that it's addictive. So when I say, I personally think that we're likely going to need to do this because I think the alternative is worse.
Yeah.
But remember, the best analogy I've heard is that it's really like morphine.
Which is, yeah.
So solar geoengineering, putting aerosols in the stratosphere, it legitimately removes some of the pain of climate change.
Yeah, but
it is possible that we could, for example, freeze Greenland and keep it from melting more. Mm-hmm. Hard to put the ice back, but at least we could keep it from progressing. Yeah. But understand that it doesn't fix the core problem. Yeah. And so it's a little bit like, you have an appendicitis. You can take morphine. And by the way, you want that morphine when they operate on you, because having serious surgery without any anesthesia, you'd be in misery. Mm-hmm. But if you only take the morphine and never actually get the appendicitis taken care of, it's a bad idea.
Yeah, there's a line from the Rocky Horror Picture Show related to that too, about affecting the symptoms and not the cause. But
that's cool. And here's the other analogy that's important. It's addictive.
Yeah.
Because once you start doing it and you keep emitting CO2 gets higher and higher. You keep doing more of it. But now, if you to stop,
it would be a lot worse. Yeah,
the climate would suddenly warm abruptly, and that would be disastrous.
Look, this has been a fascinating discussion of what is not an easy problem. But unless we talk about all these options, unless we inform ourselves of what the issues are in a realistic way, then we're not going to go anywhere. So I'm just so happy we had this chance to do some justice to the many aspects, and we could do this another time for another 2 hours.
I'm sure we could dig in more.
But thanks a lot for coming, Dan. It's been
fun.
It's been
great.
Thanks,
Lawrence.
The Origins podcast is produced by Lawrence Krauss, Nancy Dahl, Amelia Huggins, John and Don Edwards, and Rob Zepps. Directed and edited by Gus and Luke Holwerda. Audio by Thomas Amison. Web design by Redmond Media Lab. Animation by Tomahawk Visual Effects. And music by Rickolas. To see the full video of this podcast, as well as other bonus content, visit us at patreon.com/originspodcast.